So I'll make just a quick recording here. I want to present two files that contain sort of general guidelines, one about programming and one about debugging. These files contain quite a lot, so if you don't have too much experience about this, I wouldn't expect you to take it all in at once. But I'm hoping that you can make copies of the files and keep them for future use as you do further programming even after the end of the course. I think these are generally good guidelines. Being guidelines are not things you have to follow the whole time, but on the whole, if you want to go against one of the guidelines, you better come up with a good reason for doing so. So here are just some of the things. So this is something I mentioned actually today and to the live group anyway. Write your code, so if you're writing a program, write your code so that it may be easily read and understood by another person. You can help with this by using helpful mnemonic names for functions and variables, and also add comments to aid comprehension. Here are a few other sort of sound bites and so on. There's a well-known phrase, KISS, keep it simple, stupid. So at least for a first version of your program, try always to keep things simple, make sure that they're working properly and safely, and then later on you can try to do some fancy stuff. Here's a quote I quite like, apparently attributed to someone called C.A.R. Hoare, who was one of the pioneers of computer programming, best part of 70 years ago, I guess. So, he said there are two ways of constructing a software design. One way is to make it so simple there are obviously no deficiencies. And the other way is to make it so complicated there are no obvious deficiencies. The first method is far more difficult. That seems quite surprising. You would have thought a simple design or a simple implementation would be easier than a complicated one. But much experience shows it really is the other way around. Another one I mentioned today in passing is that premature optimization is the root of all evil. So this optimization, trying to make your program faster, should really be the last thing that you try to do. There are several possible uses for computer programs. Sometimes you might want to make an ad hoc program just for a quick calculation for your own benefit and so on. But on the whole, if you want to write computer code which is going to be useful not just today but also for some time into the future, so it's somehow reliable, then you need to work a bit harder. So I've been writing code for the CoCoA library, so I know other people as well. Doing so well is quite tough. There are lots of constraints. So the code needs to be portable, efficient, robust, reliable, and easy to use probably by someone else, someone you're never going to meet. They have to work out how to use it from the documentation. This one I've mentioned many times before. Absolutely. Any code other than code you're just going to use today and then throw away, always check that the supplied arguments are sane, correct, they're valid, and if they're not, report an error. Another useful guideline, this one came from Scott Myers. I hope to show you a book that I recommend by him. Try to design your functions so that they're easy to use correctly and hard to use incorrectly. And a particular example, you've got the sources for CoCoA here. So if you look in a file called numtheory-prime.h and look at a function called small prime, I think it's actually a class, and look at its constructor. I hope you'll see what I mean here as a way to make it easy to use correctly. Again, for a first version, always try to prefer robustness and correctness of your code over speed. Speed is something you will add right at the end. It's very tempting to try to add it earlier on, and you may be lucky, it may well work out, but in many cases it causes a lot more trouble than it's worth. So I'm racing through this, so I'm not going to go into any great detail. Here I'll stay a little bit more. Exceptions. I know that some people in this course have not really operated with exceptions anymore. They seem to be a useful mechanism. They're available in C++, something we'll be seeing, I guess, starting tomorrow. CoCoA has something a little bit like it. Excuse me. And many other languages also have exception mechanism. So the execution of a function may end in one of two ways. So it can either end via a normal return. So the function decides it's calculated the result and it simply returns it to the caller. Or the function may end by emitting an exception. And an exception can be essentially any value, much the same way that you can return so any value you like. In fact, return is more restrictive than an exception. A possible thing for an exception could be a string saying that something went wrong. So you would normally emit an exception if some error occurred. So then you might want to have a string saying what the function detected that went wrong. Now, normally the function, so your function that emitted an exception was called by some other function. So this other function, if it receives an exception, the normal behavior is simply to re-emit that exception to whoever called it. So we get that the exception is sort of propagating upwards. Started in one function, then it gets propagated upwards to the function that called that, and upwards again to the function that called that, and so on. This is the normal behavior. The only change to that is if the exception is caught by something normally called a try-catch block, which then tries to do something to the exception. So exceptions are actually quite an easy concept, although if you've not seen them before, they're a little bit weird. So the main point is that for many functions, there are two ways that execution can end from that function. Either a normal return, the function succeeds in calculating its value, or we get an exception coming out of it. And my experience, in most pieces of code, you don't need to worry about the exception. Your function does nothing, lets the exception propagate upwards, and someone else has to deal with it. So as I say, the usual way of, if you want to signal an error, the usual way of doing so is to throw an exception. Another possibility, Anna showed that in fact today, so another possibility is to return a sort of impossible result. But then of course that means that the caller actually has to check if this returned value is some sort of impossible value. I suggest that on the whole this sort of trick should perhaps be used only hidden inside internal implementation details. I think I might like to put in a couple of spaces here. So CoCoA-Lib uses exceptions internally, and it does so for there are two things you can do with an exception. One is you can put a useful, meaningful, helpful error message in the exception. So an exception could well contain a string which says something about what went wrong. And then in some cases, some earlier code will actually catch the exception and try to handle it. So detects this exceptions come, so it knows that something has gone wrong somewhere, and it tries to take action to handle whatever went wrong. Maybe reattempt the calculation or just print out a message. But let computation continue. So if you want to see an example of what's going on there, you could have a look at a couple of files. Maybe we'll try to do that when I show you tomorrow. There's a CoCoA's exception class that's in a file called exception.h, and a derived class called interrupt received. Anyway, we might see that tomorrow. So those are some things you need to think about when programming. Here are some more challenging goals. So this will be more for people who already have quite some experience with programming. You should try to make your code thread safe. So this is more for C++ than with CoCoA. That is, there may be two or more threads which might try to run your particular function, two copies of it simultaneously, or something like that. So the general advice here is try to avoid using any variables of global extent. So these would normally be what are called global variables or static variables. So in particular, the cout and clog and so on, which C++ uses for printing, those are actually global, so you have to be a bit careful with using those. So thread safe is one thing. Another thing is exception safe. So there are two good categories. There are more than two categories altogether, but two of them are good. One is a no-throw category. That says that this functional procedure will never, ever emit an exception. That normally applies just to the simplest of functions. Or you can give a strong guarantee. That is, if an exception comes out of the function, then all data that existed before that function was called remains essentially in a state equivalent to the one it had before the function was called. That's a little bit hard. So roughly speaking, they should be unchanged. It should not, when you call a function, it shouldn't damage any values that were passed into it. There are other possibilities as well, but really it's best to avoid those. Sometimes it may be tricky, but do try to avoid them. So in my experience, you rarely need to use try-catch blocks. There's normally not much you can do. We'll see in C++, if you need to use pointers, then use smart pointers. And these are more things we'll see when we look at C++. Last bit here, some special points for library code. So library code is code that's going to be given to other people. They will call your functions, and you've no idea what they're going to give to you. So these functions really have to check very carefully their arguments. Library code should try extremely hard never to get into a state where it causes a crash. Normally a library function should not print something out unless it's specifically for printing, or it does so because of a verbosity setting. Also, we want library code to work on all platforms, not just say, oh, it works on my computer, that's good enough. If you're going to give it to other people for them to use, it needs to work on their computer. So it was a quick rush through some hints and guidelines for programming. And now I want to have a look at some for debugging. Oh yes, so that first file was in TXT format. For some reason, this one I've written in CoCoA-5 format. So again, guidelines for debugging. So you've written your program. Let's see if it works. So first thing is to get it through either the CoCoA interpreter or the C++ compiler or whatever. That will check for certain simple sorts of errors. Usually they're called syntax errors. C++ compilers are quite advanced. They can do some fairly clever things. So even when they complain, they're usually trying to be helpful. So we have to try to get through syntax errors and need to understand what's happening there. So here's a quick example. Here's a function meant to calculate quotient and remainder, just for two integers, let's say. And what's meant to have happened is there's a typo here. I typed the wrong thing. I meant to type quat, and I typed QUT instead. I missed out the O for some reason. If we feed this into CoCoA, we will find that CoCoA-5 actually reports a problem in the third line of this function. 1, 2, 3. In this line. So not where the error is. When CoCoA reads up to here, there's nothing wrong with the program up to this point, and it has CoCoA has no reason to think that QUT is a bad name and quat is what you meant. It can't tell that. But when it gets to the next line and sees quat, it says, "Oh, I've never seen that before." You're trying to use it, but you've never given it a value, so it will complain there. So you have to be a bit careful that sometimes when CoCoA, same also applies to C++, when they detect a mistake, the true mistake was actually earlier. So in this case, it was one line earlier, but it could have been many lines earlier. So be aware of that sometimes errors are reported sometime after they really occurred, so you have to look backwards. That's one. So testing and debugging. So once you've got rid of all syntactic problems, you can actually try running your program and you can begin testing it. And of course, one always likes to believe and hope that the program's correct, but it's very easy for mistakes to get in there. And so we really need to test it. We need to try to find various given inputs that we can test it on. Some of them, so some hints here, some of the inputs should cover the easy and the special cases. We also want to test it essentially on inputs where we know what the answer is supposed to be, so we can see immediately whether the answer is correct or not. Otherwise, there's not much point in feeding in random inputs and saying, oh, well, it calculated something. How would you know whether it's correct or not? Yes, it gave an answer, but you need to know the answer is correct. So the test test inputs should also be accompanied with expected output. Now, it could also be that the exact output is not known. Maybe if the output are elements of a set, then maybe the order in which the elements appear can vary. So you have to allow for that when checking for the outputs. The output there may be a class of possible outputs. You have to make sure that you get at least one valid output here. So there's some testing there. So when you're actually testing it, you're running the program, so you also need to, scrolled a bit too far. You need to understand runtime errors. Once again, we have a similar problem to before, that the error, when it's detected, may actually be sometime after when the problem really occurred. So here's a quick example I actually ran in CoCoA. It's a bit of a silly one. So here's a list, contains 5 numbers and then a string. That's perfectly valid in CoCoA. And then we're asking CoCoA to try to sort it. So sort this list. But it doesn't make sense. If they were all numbers, then we could sort it. But a mixture of numbers and a string is not allowed. So CoCoA then tries to work on that and eventually produces an error saying, oh, I don't know how to evaluate less than between an integer and a string. And then it tells you where it found this out. It was on line 107 of list.cpkg5. That's one of the packages in CoCoA. You probably don't care what's going on in there. But what it does actually do is it gives you a backtrace as well. So this is where it detected the error. So this was inside a function called insertion sort1. That was called by quicksort1, which was called by quicksort. And then it was then called by sort, which on line 175 of list.cpkg, and that was called from top level. So top level is where we're typing commands in an interactive session. So in this case, it's nothing terribly helpful. We just know that it was directly calling the sort function, and then somehow inside CoCoA, it went through, called various other functions before it actually found the problem. So this is a bit different from what we saw before. With syntax errors, we normally want to look at the start. With CoCoA, at least, if we get these backtraces, we're typically interested in the last part of the backtrace. That's closest to where the code that we actually wrote, rather than things that are occurring inside some CoCoA package. So in this case, it was all inside list.cpkg5. So do a bit careful there. Understand how to read runtime errors. This is perhaps more of a problem in CoCoA than in C++, but we'll see more about C++ another day. Another point. Great, your program runs, it gets no errors, but the answer's wrong. That's actually a rather awkward situation. The computer's not going to help you too much in finding where the problem is. You just know there's a mistake somewhere in your program, but you've got really no clue as to where it could be. It could be anywhere. Here are some things to check. Firstly, check to make sure that the input you gave it is exactly what you meant it to be, and therefore the answer it gave you is genuinely wrong. If you gave it input different from what you intended, and you got an answer different from what you expected, well, that's hardly surprising. So really check your input. So once you're convinced the input is correct and it's definitely giving the wrong answer, invest some time to try to find simple failing cases, so simple inputs that still give wrong answers. If you're lucky, you already start off with a simple one, you don't need to do anything in 4b. If you're less lucky, you gave it, so the simplest cases worked, you gave it a more complicated one and suddenly, oh, wrong answer. So invest a bit of time trying to find one or more simple failing cases. And then you can actually start to do debugging on a simple input. You can do the debugging in CoCoA. We don't have any fancy system for helping you here. So you just have to insert some print commands in your code and try to make sure that each print command includes a string identifying where in your code it is. So I'll give an example here. Maybe sort of print loon. At loop start, we have f equal this value. So we can suppose that f is perhaps some variable that we think might give us useful information. So if you try debugging your code and everything seems okay, you could actually check, so where is the algorithm that you implemented? Where did it come from? Is there a mistake in that? On the whole, buggy algorithms are not so common. Many people read them, but it's possible there might be a typo in the algorithm, and you got to say there was an index I instead of J somewhere, and you copied that faithfully in your program, but the algorithm itself is wrong. And a computer can't help you debug this. This you then have to think about. But it's also not such a common situation. Some footnotes, we're almost at the end here. So, if you have an algorithm that uses random numbers, good luck. Debugging code that uses random numbers can be especially tricky because you run the code several times and it behaves differently on each occasion because it gets different random numbers. The obvious hint here then is if you've got some problems, insert print statements to print out the actual random numbers that were generated and used inside the program. That may then help you understand what's going wrong. We've already seen in CoCoA, this is a feature of computer algebra, that sometimes we can generate very large values, and it's possible to get computations where the values are so large that your program just becomes extremely slow, and you could say it's not really a bug in the program as such, but it stops you getting an answer. There you then have to try to come up with a better algorithm that avoids creating such large values. Again, good luck with that. That's much harder work, and the computer normal debugging techniques can't help you there. If you find a way of crashing CoCoA 5, then that's not supposed to happen at all. CoCoA 5 is meant to be completely robust. If you manage to crash it, let us know. Once again, if possible, try to find some simple inputs that actually cause the crash and then send us a file containing exactly the steps that we need to do to cause the crash so we can verify it and reproduce the problem and then investigate it. So here's a little exercise for you. Does it count as debugging? Well, we'll see. So the idea was I wanted to see estimate the probability of randomly generating an irreducible polynomial. So I've got a function here called randomized coefficients. It takes a polynomial and it gives you random coefficients in a range, let's say -9 to 9. So we start with the polynomial here. So this is you can print it out to see what it looks like, and then we just take this polynomial, randomize the coefficients, check to see if it's irreducible. If it is, we increment a counter, and then we do this 100 times and finally see what the counter is. So you could try looking at this in CoCoA, try running it, see what happens, find out what it actually does. Okay, that's all for now. Hope that was helpful. So there was a lot I've packed in here. I went quite fast. I'm not expecting you to learn it and memorize it all instantly, but I'm hoping there will be useful hints and tips here. So as I say, so for debugging, understanding syntax errors. Once the syntax errors are passed, then we have to do testing. Really try to make sure you pick out good testing examples, and ones that actually cause your code to fail. Then you keep those separately in a list because they'll then be sort of give you a future test suite, so you can then repeat those tests when you think the code's now correct. Understanding runtime errors. Not too hard, but again, you need to get used to it. Once your code has no errors at all, but the answer's wrong, again, various things you need to check and things you can do to try to make it easier to track down what the problem is. And then finally some footnotes about other particular cases and this example.